Good evening, everybody. Let's start. So we have been discussing normalizing flows. And so the basic principle is that, okay, what is the requirement? The requirement is that we want to model very complicated distributions, which are not very easy to sample from or not very easy to estimate. So what we do is we model a distribution using a mapping. So we map a simple distribution to a complicated distribution. The simple distribution could be simply a uniform distribution or a normal distribution. And we want to map it to a very complicated distribution. And we know what is the basic principle. The basic principle is that we know that whenever we do a transformation on the random variable, or let's say this is just a variable, and if we just operate upon this with some transformation, the new variable will have a different PDF, right? That we all know. How do we compute that PDF? By using this formula that probability of the transformed variable x is equal to probability of the original variable times the if you go to higher dimensions, then mod of determinant of Jacobian, or in one dimension, it is simply the mod of the slope, where u and x are related by this transformation t. And this is the simple formula. Okay, this formula is valid if it is a, what is the condition? Anybody remembers?
Invertible transformation.
Yes, if it is a bijective transformation or invertible transformation. And in case it is not invertible, then what will happen?
We'll have that summation.
Yes, you will have here, your x will map to various u's and you have to sum up all those probability masses. So in our this discussion, we are assuming t is invertible. And so this was the higher dimensional case, and these are the formula which we derived, that p of x is p of u times determinant of the Jacobian of t inverse mod, or determinant of jt mod with an inverse on top, basically 1 upon determinant jt. So this was the basic form. Now here we said, if we have a u given to us, and if we have a target x, or the probability of x given to us, can we find an optimal t which can do this job, this mapping? So we found that, okay, let's start with some invertible form of t. We started with a very simple invertible form, which was simply a line. Line means your x is equal to au plus bu, means basically a linear transformation. And we found out that the determinant, etc., are very easy to compute. But the thing is, this is a linear transformation, and a linear transformation can be very limiting in the sense that it is very less expressive. So the expressivity of a transformation means how complicated distributions, target distributions, can it model. And so this is very less expressive. The expressivity is very small, or in other simpler words, you can say it is less powerful. For example, this linear transformation cannot map my uniform distribution to something very curved. So for that, the remedy we thought of is, okay, let's have a nonlinear transformation, and how to make it nonlinear while still maintaining invertibility. So this was a clever trick to do it. And this trick implied that you don't operate all the dimensions at once. You take some dimension, let's say, in a regressive way, autoregressive way, which means you take u1, and x1 is directly u1, x2 is a function of u2 and previous x1, or basically it's linearly dependent on u2, but non-linearly dependent on u1 or whatever are the previous u's. And x3 will be linearly dependent on U3, but non-linearly dependent on the previous U's, U2, U1, etc. So that was our philosophy to construct a non-linear mapping, which is still invertible. And we found out here the inverse of the map and the determinant of the Jacobian. So these are the two things essentially which we will need, right? We need the inverse and we need the determinant of J. Now we took a very simple example. It's RNVP flow, or actually there is a class of flows called autoregressive flows, and RNVP is one example of it, but other examples are also there which are very similar. The mathematics is very similar, just computationally there can be some pros and cons, but mathematically they are very similar, very similar. So this was RNVP which we saw, and here we now, we found, this is a very nice flow. It has got some good properties like Jacobian is very easy to compute, inverse is very easy to compute. Now the only thing now which is left is how do we train the network or train the mapping. So we looked at the derivation. We thought, let's match the modeled PDF with the target PDF, or the model distribution with the target distribution. And for that, we used KL divergence to match the two. And KL divergence is a very well-known formula, very well-known quantity for you. So we have our P star, which is the target distribution, and we find its KL divergence with Px, x comma theta, where this is the modeled random variable. X is the modeled random variable, and this is the distribution of that random variable for the PDF. And then we did some manipulation. We wrote it in this form. And then we did some more manipulation, putting some more, plugging in some more values. We wrote finally this form. This is the final form, which looks very simple. So let us see what are the quantities required in this form. So we need P star X. We need PUU, which is let's say uniform or normal. So this is a known quantity. But given the samples from P star X, we need to invert them to obtain the corresponding U, right? So we need the inverse map. So this inverse map is required. Let's write down what all things are required here. So we need here, we need the samples. So one more thing I think I should mention immediately is that we cannot estimate this whole quantity. It's an integral over a very large volume, because X can be higher dimensional and P star X can be difficult to integrate. So we approximate this quantity using Monte Carlo approximation, which means expected value of a function is simply average of that function values computed over the samples from this distribution. This is Monte Carlo approximation for this quantity. And so what we need samples from P star. My pen is not working. Oh. We need samples from P star. What else we need? We need P inverse, this mapping, right? We need PU. PU anyways we have, so I think that is easy to sample. We can sample from PU, or we can obtain the value of PU. And then we need the log determinant. log determinant of JT inverse this quantity, which also we know how to compute, right? You know that this is simply the product of the sigmas. So this is also known to you. So all these things are pretty much known to you. So you can construct the loss function using these things. And that's it. Then you train your loss function. Basically, you compute the gradients with respect to your parameters phi and psi. You compute gradient of loss function with respect to these phi and psi, and that's it. And those gradients will be used to update your transformation, and finally it should converge to an optimal solution. So that's the whole philosophy of normalizing flows, or the whole theory of normalizing flows. Now, do you have any questions until here? Do you have any questions? Okay, so fine. Then let's start our today's discussion. So now see.
Sir, why is PU always a normal distribution?
No, it's not necessarily a normal distribution. It can be any distribution, normal or whatever you can easily compute. For example, normal distribution, or what is it
Okay,
called?
distribution which is easy to sample from.
Yeah, which is easy to sample from. Yes. Yes, easy to sample from and easy to compute its value. Yeah. Okay, let's, so now notice one thing. This loss function is KL divergence between P star and P estimated. Now my question is KL divergence symmetric? Is KL divergence symmetric?
No,
No, sir.
No. So then does it mean that if I use the other form, basically DKL of P and P star, will it lead to some other results? Yes, it will lead to some other results. Let me take the black pen. So let's take L theta is equal to D KL, the KL divergence between. So here we had, okay, let's say PX X theta and P star X X. So I just took the other form. Basically, instead of P star with P, I'm doing P with P star, right? So it should not be any new thing for you. Let's try to expand it and see what we are getting. Now to expand it, remember this form that here you will be writing the first term, right? If you remember this form, it is P log P upon Q. So here P will come. So now since you have reversed the two, so the other thing will come here. Okay, so I'm writing here, this is equal to expected value over P X X theta. Basically, X is sampled from this, right? And then inside the log term, right? Log of what? It is P upon Q. Okay, so this upon this. So this is Px X theta, right? And instead of writing upon, I can write minus here, right? That is also fine. This is natural log. So all log generally are natural log. P star X X. Right. Now let's see what are these terms. Okay, so now let's assume that you can compute P star X. That it's not that just you have got the samples from P star X, but you also know the value of probability of those samples. You know the PDF, you can compute the PDF exactly. So this means what I can do is, okay, so for training this, now I will be sampling, remember there was a U and it was passed through some transformation T and you got some X. So what I'm doing is, I want to proceed in this way, that I compute the samples from X or from U and then propagate them in the forward direction to compute X, right? X is equal to T of U. And then I compute P star X and then I plug all those values here in this loss function. So remember earlier, okay, so let me do one transformation, then you will understand. Can I write this as equal to with psi or phi? Psi. Can I write it like this? Can I convert this into this? The answer is yes. Let me prove it for you. Okay, let's do it from here. If I have anything like this, let's say I start from here, I can write this as equal to, let's convert the variables. Let's do a variable transformation. Let's say X is equal to TU. This is the transformation I do here. So I convert all X into U. This becomes PU integration and log of PU, basically, which means T of U, actually. Upon now dx can be written as what? Dx is equal to mod determinant Jacobian of T times du. Now, okay, X was equal to tu, so this is dx is derivative of this times du, right? So let's replace these values. Let's plug these values here. So I have got mod determinant jtu tu. Now see this term, which this was x actually. Let me put it as x only for time being. Now this and this will combine to form pu, right? This was x here. Px, this becomes pu now. This two combine to form pu. Then log the same thing times du integral. So which is equal to expected value u sampled from PUU times and of log of this whole P upon Q, basically. P of TU and Q of TU. So that's how we can write it like this. So here I will convert all these X into essentially TU. Does that make sense? I didn't do anything. I just changed this sampling from X to U. And I proved
Yes.
that how these two, pardon?
Yes.
Okay, great. I just changed this sampling from X to U and I proved that they are same. Inside the terms remain same, just that here you will say my X is equal to TU. Means you replace your X with TU. Because here, now you know the values of U, you don't know the value of X, you know the value of U, but to compute the value of X, you will apply this transformation, right? So let me write it in a more simplified way. What is this term? This term, let me use another pen. What is this term? This term is, we have computed above, our original formula. Pxx is Pu times determinant T inverse X, where basically U is T inverse X. Here we already know U. So this is Pu. This is equal to, so basically log of Pu U comma theta. No, U comma psi. Sorry. So psi is means it's an optional variable, right? You remember that, I hope. Plus the determinant term, log of determinant of J T U inverse. Yeah, you know that now this inverse can come in the front also, but anyways, so I've just, so this is this term. This term can be written like this. And this term is P star X of simply TU. You can put your X as TU. So this term is, so here you will say this X is simply equal to T of U. So now given any U, you can compute this term, right? Given any U, this term you can compute from here, PUU, simply the Gaussian or uniform distribution of U, the exact value you can compute. Then this log determinant term you can anyways compute, you know, for the RNVP, it is simply the product of the Jacobians and product of the sigmas, and the sigma is basically a function of U and you know how to compute it. And then this term is P star X of TU. You have your U, from U you will compute X by the transformation T, and then you know how to compute P star. So that's it. And you will be able to do this whole, you will be able to find the value of this loss function. And every term here is not only computable, but also differentiable, right? Here, this term, let's say this term is constant with respect to psi, but it has, sorry, constant with respect to phi, but if you have some psi random variable, you can differentiate it with respect to that. This whole term is differentiable with respect to your theta, because this is basically sigmas, simply product of sigmas, basically product of outputs, in other words, and you know how to compute them, and also you know how to differentiate them. These are simple derivatives. And this term, so this thing requires that your P star X should be a known form which is differentiable, which is, this should be differentiable. Okay, so this is, let's write down what all are the requirements for this. So to compute this loss function, you, or to basically differentiate this loss function, you will require PUU, right? You need to compute its value as well as sample, right? You need to sample from it, and also you have to know, you need to know its value for a particular U, For example, I may be able to sample from a Gaussian, but I also need the PDF, the value of the PDF for a particular sample. So both are required. And then you require, this part is done. Then you need the log determinant, basically this term which you know how to do. And this should also be in a differentiable form.
So, so how many samples do we take to find these laws?
It depends, and generally it's a large value. I mean, basically your gradient descent can be a slow process, therefore you require larger value. But here there is no restriction, right? You know the U and you can sample it as many times as you want, right? It's not limited by your data size. Like earlier, this one, if you have, let's say, 100 images, then you cannot do it more than 100 times. So yeah, you can do multiple iterations, that's all right, but or multiple epochs, but within an epoch you will have only 100 images. But here there is no limitation. You can generate as many samples as you want, right? So you need this term, and then you also need the value of, or the compute P star X for a given X. So you need to compute. You don't need to sample from this, right? You don't need to sample from this, only compute this. Whereas here you needed samples from this, but you did not need to compute this. So you see now there are two forms of loss function, and both form is useful in a different scenario. For example, let's say you are doing image, you want to learn from the images where you don't know the value of P star X, but you only have samples from P star X, then you will use this form. But let's say you are doing some other problem where sampling from P star X is difficult. I will give some examples, let's say Ising model or some models in physics where sampling is very difficult, but computing the value is very easy. So for such cases, you will be using this form.
So also, sir, since the P star X more complex as compared to PU, so sampling from PU is beneficial.
Yes, sampling from PU is easy here, but sampling from P star is very difficult. Okay. So this is the thing that there are two forms of loss function, or two kinds of loss functions. You can use any one of them to train your networks. Both are equivalent, but of course, because of numerical reasons, there can be different results, or it may converge at a different pace, or it may converge to different accuracies, right? Yeah, so that's the thing. Now, another thing which you might notice here is that in this case, okay, in this case, you require, you need TU. You need to compute the forward map. Whereas here, you needed the inverse map. Very important. In this case, to train it, you need the inverse map. You didn't need the forward map. But here, you need the forward map and you don't need the inverse map. Okay, with these, let me stop here for a while to ask you if you have any questions at this point. Okay. If not, then, so that's it. This is the theory of normalizing flows. Now what I will do is, I have two things to do now. One is to discuss some popular flows, or basically some popular transformations T with you. And the other is to program the whole thing. Let me start with the discussing some popular transformations. and then I will come to then I will come back to the programming. So basically, whatever we have discussed until now is sufficient for you to write a sample program, write an easy program, maybe just in 2 dimensions or some n dimensions. Now I'm going to discuss with you a popular flow, which is called a planar flow. It's a very simple flow, very it was one of the initial things which were used to develop this theory. Okay, there is a suggestion that it will be good if we can have an assignment to code these flows. Yes, that's a good suggestion, and I will definitely give. Okay, let me also do at this point, I will share with you something. This is the paper. It's called Normalizing Flows for Probabilistic Modeling and Inference. It's a very good paper written from DeepMind group, and they explain, they have a lot of theory which we have not discussed and which I don't find very important, at least for our normal use cases, but they are good for theoretical analysis. But this theory is very nicely explained. Yeah, they don't give much explanation of things, but if you know the meaning, then you can follow this paper. Now, since you know all the calculations and all the derivations, now you can very easily follow this paper. And I would recommend you, if you want to read more about normalizing flows, then go through this paper. Okay. I hope you noted down this name, otherwise it's recorded on cloud. Okay, let's come back to flows. So I'm going to discuss planar flows. So what are planar flows? Basically, everything else remains same. Basically, your derivations, etc., for the training and all. What changes is this thing. What changes is the transformation T. So let's say you have U, which gets transformed to X. So your X is equal to TU. I'm writing X as in a simple way, but actually it's a vector. So wherever I have written X and U, they are actually vectors. Just to save some time, I wrote it in simple way. So X is equal to TU. This is known to you. Now, this TU has a very particular form for a planar flow, and the form is this: U plus C times H W transpose U plus B. That's it. That's it. Now let me explain the meaning of each term here. So X is a vector, right? It's a vector. And U is also a vector, right? You know U is a vector. Let's say it's d-dimensional. U belongs to RD. C is also a vector. It's also d-dimensional. H is a nonlinearity. It's a nonlinear function, basically. H is a nonlinear function. And it can be sigmoid or tan H. Tan H is a popular thing used. Element-wise, basically nonlinearity, element-wise. Tan H, you all are familiar with this. It could be sigmoid also. Now, this W is another set of parameters. This is also, how do I read This is also vector RD, right? Because it is getting dot product with U. And now tell me what is the dimension of B? Yes.
R1.
B is R1, yes.
Scalar.
Yes, very good. It's a scalar. Correct. It's because this dot product will become a scalar plus scalar, and then H is a actually it need not be element wise, it's only a scalar. Okay. So not required element wise. It's a nonlinearity simply on a scalar. Okay, so that's the form of planar flow. Very simple form, right? This whole thing is a scalar. This is a vector, this is a vector, just sum of two vectors. And you can see it's monotonous. Basically, it's invertible, but there are some cases where it may not be invertible, but let's say, okay, we will discuss that. We will discuss what are those cases when it is not invertible, but we will constrain the values of C, W, B in such a way that it is invertible. Okay, so what are the learnable parameters here? What are the learnable parameters here?
W and B.
W and
Would C also be learnable?
C and B. So this is D dimensions. So basically D plus 1. 2D plus 1 learnable parameters here. Okay. Let's find out now some common properties. What all things would you like to find on this for your computation of loss function or inference, etc.? First of all is the forward map, right? Once you know this forward map, then you can sample from U, perform this forward map, and compute X for sampling new X, right? That is one thing. What else?
Inverse.
Inverse map, yes, very good. So what is the inverse of this? What is the inverse of this T? So it turns out that it is not trivial to find. It's not trivial to find, or it's not explicitly available easily. So generally, generally this flow is used in such a way that you don't need to compute the inverse. Basically, it can be used for only those use cases where you don't need T inverse. So this has this limitation. It's not very easy to find the inverse. And generally, approximations are used. Okay, so let's come to the other property, which is Jacobian. So now some mathematical exercise. What is the Jacobian of this function? How will you compute the Jacobian? Yes? Yes, how do you compute the Jacobian of a function? Okay. Okay, that's bad. I was expecting somebody will answer. So Jacobian is a matrix, right? Let's say Ij. The ijth element of this matrix is what? Right? Am I correct? Yes?
Yes, sir.
Okay. So let's compute Okay, to compute this, first let's write the whole formula in terms of elements. So my xi is equal to ui plus ci times this scalar quantity, which is h of w transpose u. So I can write it as some wj times uj, some overall j. This j and this j are not same, so let me use k then. I don't want to confuse you. K is a dummy variable which is confined to only this form, plus p, which is a scalar anyways. Okay, now let's compute the derivative. I hope you all remember your neural network classes and you know how to do element-wise differentiation. So let's compute the jij. So what is jij? Yes? Somebody would like to speak out? So the first term is ui, and derivative of ui with respect to uj will be 1 only when I and j are same. So let me call it as delta ij, right? It's a Kronecker delta function, plus ci is a constant, and this thing is a function of uj because sometimes the k will be equal to j. This thing can be a function of, so let us write as h, let's say whatever it is, whether it's a sigmoid or tan h, it will have some derivative. So let's write it as h dash with respect to u, and so basically this is, I will just write it as w transpose u only plus b times the derivative of u, this internal, this thing, right?
Yes,
W, yes. W what?
J.
J.
Very good. So this is your Jacobian. Now, you can write it in terms of matrix also. J is equal to what? This is identity matrix, right? And this is Ci times Wj, and this is a scalar anyway. So let me write it as h dash W transpose U plus B. This is just a scalar thing. And then the Ci times Wj can be written as the vector C times the vector W transpose. No, C transpose, right? W times C transpose, because oh, am I writing it incorrectly? Oh, actually it's Ji. I'm sorry. Ji, because X, okay, J's are the rows and I's are the columns. Yes, now it is correct. So this is Ji. And this is anyways Ji. So Ji, so J, so W comes first. And C transpose. Yes. Yeah, this is the Jacobian. Now I have to find out the determinant of Jacobian. What is the determinant of Jacobian? So for this, I have to use one identity. This is called, I think, Sylvester theorem for Jacobians. I forgot the exact name, something Sylvester. If you want to find out, just do Wikipedia. Wikipedia has the exact name, Sylvester for determinants. Sylvester identity for determinants, probably. Okay, so then what does it say? It says one, okay, I plus AB, the determinant of this is equal to determinant of I plus BA. I plus BA. I plus AB and I plus BA, they are same. So let's say A is n cross m, B is m cross n, and I is n cross n here. So here, this is m cross n, this is n cross m, so this is m cross m. Can you use this identity to find out the determinant of this? Yes. So basically you will be converting this into C transpose W, right? C transpose will come to the left-hand side. So this becomes plus something plus. Now what is this something? This is m cross m. So this is d cross 1. Right? This is d cross 1. This is 1 cross d. So this is d cross d. Now, but when you do the reverse, then this is 1 plus same h dash w transpose u plus b times c transpose w, which is a scalar now. See, computing this determinant is very easy. C transpose W is a scalar. Actually, C transpose W is also equal to W transpose C. It's just a dot product. So anyways, so that thing. Yeah, so that's it. So this is the determinant. And it's very easy to compute, as you can see here. Now, what else do we need? That's it. That's it. Okay, now here, one thing we discussed, that this function is always invertible, and this is not always invertible, but it is invertible when it is monotonous, when it is monotonic. Monotonic means it's either always increasing or always decreasing, which means its slope is either always increasing or always decreasing. So to ensure that in the higher dimensions, it means my Jacobian should never become equal to 0, right? Basically, which means my Jacobian is always invertible. If my Jacobian is invertible, then my function is invertible. Okay, so my Jacobian should never become equal to 0. Jacobian is equivalent to slope in the higher dimensions, right? So my slope should not become 0. It should either stay always positive or always negative. So let's put that constraint here. So for invertibility, we generally don't put a necessary condition. We just make a sufficient condition that if you ensure this, then definitely it will happen. So the invertibility condition is this term, 1 plus this whole thing should be always greater than 0, right? Which means,
Excuse me, sir.
yes,
Should it be greater than 0 or just not equal to 0?
yeah, I'm putting a sufficient condition. I'm not making a necessary condition. I just want a kind of condition which will ensure that my function is invertible. But of course, there can be other conditions also where it is invertible, but I'm just finding one of those.
Okay.
I can say a sufficient condition, which is very easy to compute. So you can see here that when this whole thing is greater than 0 always, then this will be definitely invertible. So I will say 1 plus h dash C transpose W is greater than 0, which means let's now see h dash is a scalar, and h dash will have some values, and we can say so let's put it like this. Let's take 1 to the other side. Then it becomes C transpose W should be greater than minus 1 upon h dash. And basically h dash is a function of some A, and I can say supremum of A. So if this thing is greater than the smallest value of this term, then we are sure that it will always be greater than this, right? Or we are always sure that this will always be invertible. Right? Is that clear? This is just a kind of very easy condition to derive. It's not the necessary condition. There can be some other conditions also when the Jacobian is invertible, but this is just one of those conditions. It's a sufficient condition. Okay. Now, that's it. This was all about the planar flows. Anybody has any questions here? Now you can plug this flow into your previous formulae and you can easily derive all the things, maybe forward pass, reverse pass. Reverse pass is all not possible. The inverse is not trivial, or it's not easy to compute. So, but the other things are possible. So basically you can use it. Okay. If you are using this form, you need a T inverse. So you cannot use it. If you're using this form, then you don't need a T inverse, so you can use it. But then there is a trick which people do. And the trick is that they use this planar flow, the form, to model T inverse, not the T. They use this form to model the inverse map. So in that case, they can use this, but they cannot use this. I mean, okay, these are some details, right? When you know that you only want to compute in one direction, then just take this form as that direction. So, okay. Yeah, but yeah, this has one limitation that you cannot use it both ways. Okay, but this is a historical kind of development because normalizing flows were developed and planar flows were an important way to find your normalizing flows. Okay. Now,
So,
similarly, yeah.
so I had a question. What is the meaning that they take it in the other direction? Means they write it as u of tx.
Yes. So basically, u is equal to t of x.
Okay.
Means like this. U. So computing this map is not easy with planar flows, but computing this map is easy.
All right.
So this means if you are using it in this way, then you cannot sample from X efficiently, right? So, but this can be used to estimate the some other things. Means it can be used for some other applications which don't require you to sample X. It can be used to compute the probability of X. For example, if you want to compute PXX, then you know the value of X. Now use this map to compute the value of U and find PUU, and you know the Jacobians. So very easily you know the value of PXX. So basically to compute PXX, but can't sample X. Okay. But here you can sample X efficiently, but computing PXX will be difficult, right? So here sampling is easy. But with this one, sampling is easy, but computing PXX from X is not. Of course, if you know U, if you are obtaining this X by sampling, so you know U, then it is easy. But if you don't know U, then it is difficult. So for example, you are given the image, let's say X is an image, and I want to know what is the probability, then this is not easy. But here it is easy. Give me the image and I can tell you what is the probability, but I cannot give you similar images. I cannot I cannot sample similar images. Okay, this was the planar flow. Something similar is another flow which is popularly used, similar to planar flow. It's called radial flow. It will be a nice exercise if you can compute this mapping. Let's say take your x as a scalar or something. This is your x and this is your u. Oh, no, sorry. This is your x, this is your u. And if your u is something, your x will be something. Some kind of mapping will be there, which will be bijective, but it will be of some form. Okay. And you can also plot, let's say your PUU, let's say this is U1, U2, and this is some PUU in this plot. Then how will it transform to some PXX using the planar flow? So this will be some kind of form. Let's say this is a Gaussian or uniform distribution. Then how will your PXX look like? You can make these plots and maybe do it as an assignment. I may not grade those assignments, but if you do it, then maybe in the quiz or exam, I can ask you. Okay, let's come to the radial flow. Just give me a moment. Okay, so radial flow. What is a radial flow? It has also a form, just like we had for planar flow. My x is equal to tu, and this is equal to u plus beta times u minus u naught divided by alpha times, alpha plus r, where r is equal to u minus u naught Euclidean distance, or the L2 norm. This is the radial flow. Here, okay, now what is u? U is, it belongs to, let's say, RD. Beta is a scalar. Or it is simply a real number. Alpha is also a scalar. And u naught is also RD. Just like u is RD, u naught is also RD. And R is again a scalar, right? R is just a scalar. So how many trainable parameters or learnable parameters? How many learnable parameters are there?
D plus 2.
Okay, so we have beta, alpha, and u naught. So which is 1 plus 1 plus d. So d plus 2 learnable parameters. Good. Now let's compute the inverse. What is the inverse? I think it's very difficult again. Very difficult, non-trivial, very difficult. Again, you will use some approximations. If at all you want to compute it, you have to use some approximations. But generally, people don't compute. I told you that people use it in a clever way that they don't need to compute the inverse. Or they don't need the inverse. Okay, now let's come to the Jacobian thing. What is the Jacobian of this?
So,
Yes?
Sir, is inverse needed at all? I mean, we are introducing these flows to sample from a complex distribution.
Yeah.
So why would one want to go from a complex to a simpler one?
Okay, good question. Good question. Why would we need the inverse? Okay. Let's say you have an image, you have images of a person, and now you want to make a flow such that you can compute, you can sample more images of same person, right? You can generate new images of the same person. Or you have some distribution, you want to generate more samples from the same distribution. So in that case, you don't know the value of P star X, but you know the samples from P star X. So you have to stick to this form. And now you know you have to have T inverse because you want to train the model, but you also need T because you want to generate more samples. So you need both T and T inverse, right?
Got it.
Yeah. So it depends from use case to use case. So basically planar flows and radial flow cannot be used for that particular use case, but it can be used for other uses. So therefore, okay, let's compute the Jacobian. So please compute the Jacobian. J is equal to dou x I upon dou uj, and this is ji. So what is my x in terms of the elements? Xi is equal to ui plus beta times ui minus u naught I upon alpha as a scalar plus, so r is basically under root of ui, no, sorry, it should be summation, sorry. It should be summation over some dummy variable k, uk minus u naught k, uk minus u naught k whole square. Right. Can you quickly compute the Jacobian? I can also do it, but okay, it was just a good exercise. So derivative of xi with respect to uj, so this will be delta ij or delta ji, both are same, plus this is here is a ui and here is a uk. So you have beta upon this term, which is basically alpha plus r. I will write it as alpha plus r only. And here you have delta ji again, right? Plus, now I have to do the denominator one, beta ui minus u naught I, this remains same, upon, this is 1 upon something, so this is minus 1 upon this whole square, right? So this is minus 1 upon alpha plus, I'll call it as r only, r whole square, right? Times the derivative of this. So what is the derivative of under root of something? It is 1 upon twice of that thing, right? 1 upon 2r basically, times the derivative of the thing inside with respect to j now. So this will be twice of uj minus u naught j. Am I correct? Did I do any mistake here?
It's correct.
Shouldn't be there one more minus sign?
One more minus sign for what?
for the square root differentiation.
1/2.
No, sir. No, sir. It's right.
Yeah, should be fine. Let me check. I don't know. Let's see if there's a negative sign. Yeah, there is a negative sign in the derivation as well. Yeah, there is a negative sign. I am just checking in the paper. In the paper, they didn't give the derivation, they just gave the form. So yeah, there is a negative sign here. So we are on the right path. Yeah. Okay, so this becomes what? This is in, if I write it in the as a matrix, this is I, right? This thing is I. Let us take this as common. 1 plus, then this is just a scalar, beta upon alpha plus r. Plus, oh, minus, sorry, minus beta times, now this is u minus u naught, and this is again two cancelled. U minus u naught, u minus u naught. So this is ji. So this term times this term. So this is basically u minus u naught times u minus u naught transpose. Right. So it's a matrix, and divided by alpha plus r whole square times r. Okay. That's the whole derivation. Now we have to compute the determinant of this Jacobian. So you have to compute determinant of Jacobian and the mod as well. So what is this? This is now complicated. So I'll be using some identities here, which are directly the identities of the determinant, the properties of determinant basically. So if you want to compute determinant of some constant times A, let's say some constant times some matrix A. So here alpha is a scalar and A is let's say, this is, let's say, m cross or n cross n. Then what is the value of this? Yes?
Alpha to the power n into that A.
Very good. Very good. Alpha to the power n and determinant of A. And we have discussed the Sylvester identity, which is determinant of I plus AB is equal to determinant of I plus BA. So these two things I'll be using to compute this. So, but okay, so there is a scalar here, right? There is a scalar, and there is an identity. So scalar times identity, and here also this is a matrix on the top, and then this is some scalar. So it can be converted into this form, but the only limitation is that there is a scalar thing here. So let's try to take this scalar out, common. So this becomes equal to 1 plus beta upon alpha plus r, right? Let's take this as common. Then I'm writing j only first. I minus beta times u minus u naught, u minus u naught transpose upon alpha plus r whole square r, and 1 plus beta upon alpha plus r. Does that make sense? Nothing non-trivial or nothing difficult until now, right? Now my U is d-dimensional, let's say U is RD, then this will become equal to, so when I take determinant of this thing, this determinant of J, this is equal to 1 plus beta, this is a scalar, right? 1 upon alpha plus R, this to the power capital D. And then the term inside, so what happens here is, this is I plus, so let me write it down. This is one matrix, this is another matrix, A, B, right? So this becomes BA. Everything else is scalar. Just note, everything else is a scalar. So that doesn't play any role here. Okay, let's write down. So this is, when you take BA, then this is basically D cross 1, 1 cross D, then this becomes 1 cross 1, 1, minus the scalar term beta upon alpha plus R whole square, R 1 plus beta upon alpha plus R, times U minus U naught mod square, which is basically equal to what? This is what?
R square.
R square, very good. This is basically R square. So R square is, okay, there is one R square here, there R here, which gets cancelled. So let's now try to simplify this. This becomes equal to 1 plus beta upon alpha plus R to the power D. Then you have here, okay, let's try to take the denominator. This becomes alpha plus R whole square times 1 plus beta upon alpha plus R minus beta R, and divided by this whole thing, alpha plus R whole square times 1 plus beta. So this becomes minus 1, right? Now let's try to simplify this. This is equal to 1 plus beta upon alpha plus R to the power D minus 1. And then this term goes inside alpha plus R whole square plus beta times alpha plus R, only single alpha plus R. So beta times alpha plus R minus beta R upon alpha plus R whole square. So now this beta R gets cancelled with this beta R. So we get a very simple form. 1 plus beta upon alpha plus R to the power D minus 1. And then this is, both are same. So 1 plus beta times alpha upon alpha plus R whole square. That's it. That's it. So this is our final form of determinant of Jacobian. Very simple form, right? Imagine we started from very apparently very complicated, but we finally are able to derive something very simple. You can compute the complexity. Let's say if you want to compute the value of the determinant of Jacobian, what is the complexity? It is O OD, right? D is the dimensionality of our U, right? So this complexity is of order D, computational complexity, right? As the size of your U increases, or equivalently, if the size of your X increases, then this Jacobian will scale linearly. The complexity will scale linearly. It's a linear complexity. Yeah, that's it. So anything else? We have covered the radial flows. Okay, fine. Though we can stop here now. It's 6:30 already. Now, what next I want to discuss with you is how do we do the coding? How do we program the whole thing into? I would request you to do the program and write simple program in TensorFlow. Very simple program. Already there are some existing libraries, but I would request you not to use those libraries. You can use the neural network libraries like Keras, etc. But don't use the TFP, TensorFlow probabilities, and it has got some implementation of normalizing flows already. But I would request you not to use those implementations. So it has got something called bijectors and some things like that. So maybe if you don't use that and you try to implement it on your own, that will be a very good exercise. You can start with a very simple example where you are having a two-dimensional U and a two-dimensional X, and then you can use simply an RNVP thing. But the thing is that you may need to do, if you remember the trick where you first compute in one way, then the other way. Yeah, so here you first do it, where it is. Oh, it's not here. Okay, first you apply, no. Yeah, first you apply it in this way, then you flip the two and then apply in this way, then again flip, applying. So maybe you may have to do multiple layers, but that's also very easy. Okay, thank you very much. We stop here. Come with your questions next time and bring your implementations in the next class. Thank you.